Okay, so today we are going to start look at these conditional PMFs. Given some event, right? So I'm going to restrict this to the case that omega x to start off with is right, a bunch of is a set of non-negative integers, right, and A is an event of the type x is greater than m, right. This could be 0 also, does not matter. Okay, let me write it like this, does not matter. Right. Whatever we are saying here, right, can easily be extended to arbitrary events of the type a less than x less than b and so on. I am just doing it for x greater than m for because I need to take some concrete example and I do not want to just do it in very general terms, right. So, so I have this event a x greater than m and I am interested in, we are interested in finding the probability how the probabilities of x vary if given the additional information that x is greater than m, that is this event a has in fact occurred. So, when this event with the information that a has occurred, then how does the PMF of x change, right. So, we have the conditional PMF. Let me write the conditional probability P of, let us say, x equal to k given a. This is what we want. Correct. Okay. So, if I take any a as is clear, this is not, you cannot go beyond this, but for this particular a and for example the geometrical PMF, we can derive a very interesting result, right. So, it is what I am going to look at now. So, basically, right, we have i.e. this conditional probability by the rules by the definition of conditional probability is what? So, is clearly exactly the same as what we had earlier. Right. The numerator, what can you say about the numerator? What will be the value of the numerator if k is that number k is smaller than or even equal to m? It will be 0, obviously, right. If you are given the fact that x is greater than m, x cannot be smaller than m or even equal to m, isn't it. So, clearly this is going to be 0 for let me say less than equal to m. And this is just an example, this is not right, this is also an example, right. Okay. So, what about the right the case that k is greater than m? In that case, it turns out that this is a subset of this, right. X equal to k is a subset of x greater than m. If you take k equal to m plus 1, m plus 2, whatever, right, you are only taking one value of k at a time. Okay. X equal to k is you are considering only one possible value. So, that is obviously a subset of the event a. The event x equal to k is a subset of the event x greater than m. So, this will be what? This will be simply probability of x equal to k divided by the probability that x is greater than m for k greater than m. And these, we want to write this conditional probability in terms of the PMF of x. That's our goal. So when I say omega x, I also mean I also assume that the PMF is given, right. So what happens here now, or note that x, what is the probability that x is greater than m? This is simply the denominator there. This is greater than, right. This denominator term is what? This is going to be in terms of the PMF, the summation from. So in general it can go up to infinity of Px of, well, let me not use k here, I am going to use some other dummy variable of summation. I should use, say, L or whatever. Could use I, anything. And the numerator is just the unconditional PMF, or whatever you started off with, right. So this probability of x equal to k given x is greater than m is basically Px of k divided by this. And it is 0 for k smaller than or up to m. In the geometric case, what happens? No, before that let me introduce some notation here. The notation we need to use is, if you look at this, so this is, right, a function of the index k, or the parameter k. So this, if you consider the collection of all these conditional probabilities, it is called the conditional PMF. Just like these guys are the basic unconditional PMF that you start with, the collection of all these probabilities, right, from L going from whatever 0 to infinity or 1 to infinity, which as the case may be, right. So here these probabilities are conditional probabilities, and the whole set of them is called the conditional PMF. So the conditional PMF, right, of x given A is basically the collection of. Now we need to write some okay, let me write it like this, P of x equals, just I will rewrite this. Just take this exact thing and put it here. So k, whatever, k equal to in this case m, let's say m plus 1 to infinity for this, it has to be only that, right, since this is x is greater than m, and we have said x is omega x is a set of integers or some non-negative integers. This has to be from n plus 1 to infinity. Okay. The understanding of course is that it is this, you can also extend it, put it from 0 to infinity with the understanding it is 0 for k less than m. Anyway, so but we need some more compact notation. The more compact notation that we will use in this course is, right, for this guy you write it as P of x given small p of x given A. This thing is written as a subscript, right, x vertical bar A, then you put the argument k just like you had this L out here, and then you can optionally indicate the event, which is useful to do, because you do not know what the event A is unless you go and look at the context. But since there is space here, typically it is always, this is in more often than not the event A is in fact indicated this way with a vertical bar after the k and So, please use only vertical bars here, no slanting bars, no up and down kind of thing, it's all in the same line. That is, this is a subscript line and this is the argument line. So, what is the notation here? More compact, let me write here, more compact notation is this. Is this clear? X given A is a subscript, right. So, for people that want to try your hand at late taking the subscripts and so on, it is very easy to do, right. All you have to do is put this whole thing as one subscript string, and then this is the argument string, right. Okay. So, this is true for the general case. For the geometry case, something very interesting happens, right. So, okay, so we can proceed to that, right. So, I think this is fairly clear, there is nothing no, there is no deep nothing deep stuff happening here, just conditional probabilities just collected together and called the conditional PMF. That is what we have done. For the geometric case, so for that is, assume these will not change, right. Of course, the 0 may or may not be there, it is not a big issue, right. What happens in the geometric case? Now, this is where I am going to introduce some notation, extra notation in the sense I need something to indicate the PMF of a random variable, right, and for that to meet that requirement, right, it is written like this. You write the name of the PMF in some form, we can expand it in full geometric P, and you use this tilde notation to indicate that this random variable X has this PMF or later on PDF whatever, right, and this geometric I am writing out in full because there seems to be no universally used or universally accepted shortening of geometric or Poisson or binomial. So, it's you might as well write out the full word, right. Only negative binomial is a little on the long side, but if we ever need to do this for the negative binomial, we can think about how to, let us not worry about that situation right now, okay. So, in this case where and this P is a parameter of the geometric PMF. So, here, so this tilde notation, right, is going to come up a lot from now on, right. It is a very compact way of saying of telling what is the distribution of X, of indicating the distribution of X, right. So, now this when X is geometric P, then what is the probability that X is greater than M? This we already did. This is 1 minus P to the power what? This means that no success in the first, I mean X starts only from 1, does not start from 0, does not matter, right. You can always say that 0 has 0 probability, it is not an issue. But what is this for any M? We have a nice closed form expression, no? What is it? 1 minus P? Come on, we did this not last week or earlier part of this week, last week I guess. 1 minus P to the power of M. Why are you giving me such blank looks? These are things you should immediately say. And it is valid for all, even for okay, maybe I should say for M greater than 2, or is it M greater than 1? Can I say that it is valid? No. So, for M, it's in fact it is true for M equal to 1 also, because X greater than 1 is perfectly valid, right. That means that is the first toss or the first trial is failure at M equal to 1. So, this is perfectly valid for M equal to 1 as well, there is nothing wrong, right. It is valid for all values of M as given here. Now, go back to and what is the go back to that thing with Px. What is Px of k? This we already know as 1 minus P to the power k minus 1 times P. for again k greater than 1. So, what is the ratio? P of x given A of k given x greater than m is what? Please do it. What do you get? What do you get? Tell me. 1 minus p to the k minus 1 minus m times p. For what values of k? K has to be greater than m or k equal to m, greater than equal to m plus 1, whichever way you want to say it. How do you compare this and this? This is the unconditional PMF, this is the conditional PMF for this particular event. What is the, what can you say about these two? This is just a shifted version of this. This sequence is a shifted version of this sequence. You're just moving it to the right by m samples. In other words, the whole PMF is pretty much preserved intact, except that it's just shifted. This is a shifted version. This whole thing is a shift of the unconditional PMF. This is the so called memoryless property of the geometric distribution. In other words, I can write it without using English, just write it in mathematical terms, right? In mathematical terms I get, let me if I want to write Px, what would I write here? I would just write, what would I put here? K minus m for k greater than equal to m plus 1. So that in one line encapsulates the memoryless property of the geometric PMF. Why do you call it memoryless property? Because the fact that you didn't get any success in the first M trials does not have any bearing on how the successes or failures will evolve after that. You're back to the starting point pretty much. What happens in future is has no connection to what happened in the past. Right? So, is this clear? So, just remember this one line tells you everything about, right, this particular feature of the geometric PMF, and it is not shared by other discrete PMFs, right. In particular Poisson, as an example we will look at that also. Supposing I use x tilde x is Poisson with parameter lambda. Now it turns out that I do not have a closed form expression for Px greater than m in this case, but does not matter, I do not need a closed form. Now one of the goals in this course, especially for IIT students, not necessarily the online version, is that, right, you people should use mathematical tools to evaluate these things, right. If necessary, if called upon to do so, you should be able to write a small program to evaluate given numerical values, right. Although a closed form expression is not available here. What is a closed form expression I am looking at? Px greater than m is what? Some summation, once again it is the same old thing. Now instead of writing Px of L, I will just put the exact expression. This is what is Px of L in this case? Is e to the power of minus lambda power L divided by L factorial, L going from what? M plus 1 to infinity, right. All I know is that this number, right, is smaller than 1, it's more than 0, smaller than 1, that is all I know. But I do not know what it is. So, this has no closed form expression. Unlike the geometric case, there is no closed form expression here. But doesn't mean that one of the things that you have to remember, just because something does not have a closed form, an integral or a sum, does not mean that it does not exist, it very much exists. What is the meaning of an existence of a sum? It means it converges, that is all, or an integral, right. There is no nothing more to it. Existence is just being finite, which is, and this is definitely finite, has to be between 0 and 1. Now, so what is this? So, I can write it out, no, I can write out this e power minus lambda power k divided by k factorial, this is the numerator, is not it, and then the denominator is all of this. Let me not copy this whole thing, I will just write Px greater than m. So, basically what will happen is the only simplification that is possible is this e power minus lambda will cancel, that is the normalizing term, otherwise nothing, you will not get anything else, any other simplification. So, of course you should always put that. So, this is not equal to Px of k minus m by any stretch of the imagination. So, do not think that this, so just because it happened, and in fact it turns out only the geometric PMF has that property among the discrete distributions, right. So, the Poisson does not have that property. If you cut off the head of the Poisson distribution, you cannot recover the rest of it, but if you cut off the head of the geometric distribution, you can recover the rest of it, that is what that is saying. It's right. So, the geometric distribution, the head of its head is like the lizard's tail, right, you cut it off, it regrows, right, it's so like that, right. This says that the head of the geometric distribution is, there is nothing special about it, you can recover whatever it is from the remaining, right, remaining bits of the sequence. Poisson, that is not possible. Here again you do the same thing, it completely changes, right. So, remember this conditional, so okay, to summarize this whole thing, I am not going to take any more examples because I think this one example is good enough, right. The conditional PMF is as valid a PMF as any other PMF, right? It is a valid, if you add up all these probabilities from m plus 1 to infinity, you will get 1 again. Why will you get 1 again? Because the numerator and denominator will both be Px greater than m. So, it has to cancel and give you 1. So, the bottom line which I am going to, which is really well and truly a bottom line here, and that is coming at the bottom of the board, right, is that conditional PMFs are valid PMFs. Put this valid in big uppercase letters. But the domain of the PMF or the support of the PMF will change. It is not going to be the original 0 to infinity, it changes. Supposing I use a different conditioning event, say the event A is that x turns, I am going to condition on the event that x is between 1 and 10, then the conditional PMF will also exist only for 1 to 10, it will not exist outside that, because you have been told, right, that x is taking a value between 1 and 10. Only thing is this event A here, the conditioning event always has to have positive probability. You cannot condition on impossible events with 0 probability. That is the only thing you have to watch out for. Otherwise, any other kind of conditioning is possible. Indicator random variables are also very useful in many situations, right. So, basically they are Bernoulli random variables which are connected to events, that is all they are. Right. To specific events. So, this these allow you to right, to convert an event into a random variable essentially. Very simple. Instead of saying the event A has occurred or not, you say, well, the indicator is 1 or 0. You can say they are associated with specific events or connected to the specific. So, I can have another either way of understanding is okay. So, e.g. Supposing I consider an event A on some probability space, it does not matter, A can be any event in any probability space, right. This will give me the indicator IA. Usually you always use the letter capital I, uppercase I to indicate the indicator, right, and the subscript A to show the event that it indicates. So, what do you want of this IA? You want probability of IA equal to 1. So, IA you want, what do you want it to be? You want it to be Bernoulli with what parameter? What is the success parameter of this Bernoulli? P of A, right. So, probability that IA is 1 is exactly P of A, and probability that IA is 0 is 1 minus PA. More formally, in terms of the sample space omega and capital omega and sample point small omega, right, you say this, that IA of omega, right. Now we are going back to the definition of a random variable as functions of points in a sample space. When, so IA of omega is just 1 or 0. So, for each point small omega and capital omega, right, this random variable IA either takes you to 1 or to 0, no other number. So, when do you, right, when do you give the value 1? You give the value 1 if omega, or let me say for omega in the set A, otherwise you give it the value 0. And there is no other, right, possibility, either omega is in A or in A complement, right, A and A complement are a partition. So, there is no other, right, they cover the space. So, you do not have some third possibility that is neither in A nor in A omega nor in A complement, and this is a complete definition. So, if you look at this clearly, probability of IA equal to 1 will be P of A itself. So, these indicators are a bridge between events and random. You can always introduce a random variable to in place of an event essentially, and they do have, we will look at them definitely in more detail in the course. I thought this was a good time to introduce them because we are looking at all in many possible, right, situations of discrete random variables, and this is surely, right, a place to talk about them. So, you can do it for any, you can define indicators for any event you want, right, can define IAB, anything, right, IABC, etc., that is the power of the indicator, right, that they can be defined for just about any event you wish to define them for, and then there is a lot of manipulation you can do because we will come to that later, right. Just note that they enable many calculations to be vastly simplified. That I will save for a later time, right, because we have not yet talked about manipulating random variables yet in a formal way. So, after we do that, we can look at how to use this indicator. For now, we are just defining them. Okay.